Okay. Yes. Okay. This is the last part of lecture number 1. Welcome, everyone. So I'm going to finish our discussion on polynomial regression, which we started from last meeting. So in the polynomial regression, what we are saying here is that we want to estimate a function. Okay. In this case, you want to give the data points some function that will have the best estimates of the behavior or of the characteristics of the data points. So in our case, these data points are generated artificially. Okay, so they are based on sinusoidal function. Okay, sinusoidal function with some noise being given. Okay, that's why there is this some data points on the sinusoidal function, some data points outside of the sinusoidal function. And now the point is, we want to give a polynomial function. We want to use a polynomial function that will give a best estimate or a good estimate of these data points. Okay, so that is what we are trying to do now. So given x and t, x being the x-axis, horizontal axis, and t being the target points or the values. Okay, so now what is the polynomial? We know this already, the equation of the polynomial with weights w0 and an input x, x1, w1, x to the 1, w2, x to the 2, or this equation. Okay, the summation of all the weights multiplied by the input. Okay, so now the question is, what is the value of m? Okay, what is the value or the degree of your polynomial? Okay, that's the first question. And what are the values of your w? This is the second question. Okay, now we say that, for example, in this case, the same data points that are given to us, there are many ways we can estimate. One is just a horizontal line where your m is equal to 0. So when your m is equal to 0, you're just using the first equation, or the first, the first term of the equation. So you say your y, okay, maybe, can I move this one here? Okay, move there. And also this one, I want to move it so that it doesn't bother me there.
We can't hear you, sir.
Sir, your mic is off.
Okay. Since when is my mic off? Just now or no?
When you started the formula.
Okay. Okay, I think I pressed the wrong button. So now let's do again. Okay, so here. So in this case here, this is our y, which is the output, and the input are x. Okay, the inputs are the x, which is the input parameter, and then we plot it as the horizontal axis, and then the other input is the vector w, which is the weights of the polynomial. So now that we say that you have a0 to the x0 plus a1 to the x1 and so on. So where your index of your weights a is equal to the order of your input x. Okay, so we can have am up to am, okay, x to the m, where m is the order of your polynomial. So now we want to know, in this case here, those points that were generated by the sinusoidal function with noise. We want to know what would be, how can we estimate these data points given different m values. So if m is equal to 0, m values for the polynomial function. If m is equal to 0, then you'll just have this term. Okay, this term only. Okay, x0 is equal to 1. So you'll just have a flat line. So we know that there will be several, depending on the value of m. It could be down here, or up there. Okay, those are all the other m's, but it will remain, I mean, those are all the other lines when m is equal to 0, but it will remain just the horizontal m. Okay, so we know, okay, hold on. Hello, Dr. TJ.
How are you, Prof. James?
I'm having a class now.
Oh, sorry.
Yeah.
Later.
Later, yes. At 3 o'clock. Yeah, thank you. Bye. Okay, hello. So now, now we have, so we say this is the first point, and then there's a horizontal line. And now, when we say the second, we say order is m is equal to 1. So m is equal to 1. So that means the maximum order is 1. So all these two things are included. So now we have a line, not just a horizontal line, but a line with a slope. So in this case, you have a line like that, you have a line like this, you have a line like that, okay? So we want to know which line is has a better approximation. The next order is equal to 3. So order is equal to 3 up to here, okay? Up to here. So now up to there. So in this case here, this is the, okay, it could be like that, yeah. It could be like this, like that, or it could be the other way, like this, okay. Okay, so those are the other combinations. And we see, we were going to see which one is a better approximation. Now, if we increase the m, for example, in this case, m is equal to 9, you see that all the points, all the points go through the function, which is the red line. But then it's called overfitting because, yes, it fits into the points, but beyond the points, the estimation is very bad. For example, at this point here, it doesn't estimate very well. It's very far, for example, here. So the function estimates that here at x is equal to, maybe this is 0.1, then your target value is around 2. That's very bad, but in fact, it is only around 0.5. Okay? The correct value is around 0.5. Okay, but here your value is 2. So this overfitting can be good only in the training data or the data that is available when you are trying to build your polynomial function. But outside of those data points, it can perform very badly. Okay. Now, so how do we know that we have a good estimate? That is what we are trying to do here in this lecture to finalize this session. So we know that we have a very good estimate when the error from the target value versus the function is small. So in this case here, this is the target value. This is the target value, okay? And this is your function, okay? So this is the error. Okay, so in every point, there's an error in this case. Yeah, this is the error also, and that's the error. Okay, well, if your function went through all the points, for example, like this, if this red line went to this like that, like that. Well, there's almost zero error, yeah? Almost zero error, but the problem again is overfitting. That means outside of that function, for example, somewhere here or somewhere here, we don't know, yeah? Okay, it could be a very bad estimation. Okay, so how do we measure this? Okay, our error term is given as this one already. So we know that this is the value of the function minus the target value squared. We discussed that one already, that this is the error squared. So the error is squared, error 1, and then sum up with another error, error 2 squared. Okay, sum up with another error 3, okay, squared. So we have all those errors, okay, against the function minus the target value squared, and you sum them up, those are the errors. So we've answered already the question why you need to square it, so that, you know, the errors don't cancel. Okay, you add up all the errors instead of canceling if there are negative and positive errors. So the 1/2 is just for convenience, in order for us to get rid of the terms when you are going to take the derivative of this. So we're saying that in order to minimize the error, last meeting, in order to minimize the error, we are saying that we take the derivative of the error function. Okay, so this is the error function, this is our polynomial function, and this is our error function. Now we want to take the derivative of this error function. Okay, so now if we take the derivative of this error function, how does it look like? Okay, the derivative of that error function is shown here. The derivative is shown here. So if we take the derivative of E here with respect to W1, how does it look like? So this one, so we know that if you take the derivative, for example, we take the derivative here with respect to W1. Okay. So what is that function? Okay. What is that function? Okay. There's a 1/2. Okay. You take the derivative, you take the 2 here. So each term has a 1/2 term. Okay. So let's just write it out. You have y in terms of x, okay, 1, and w minus t1 squared plus 1/2 of y x2 w minus t2. We are just spelling it out. You understand this? This one is equal. And we take a dot here. Dot here. So that in our case here we have x to the m. Okay, so x to the n, because those are the data points. X to the n, w minus tn, okay, squared. Now, how do we take the derivative of each term? We take the derivative of each term with respect to W1, because we go through W1 up to the M value. So For example, if your m goes to up to 5, then W1, W2 up to 5. So you take the derivative respect to W1, W2, W3, W4, W5. Okay, so let's just take W1. Okay, now if you take W1, then what is this term with respect to W1? What is the derivative of this one with respect to W1? So these two will go here, right? Will cancel. Okay, and then this whole term, and then the derivative of what's inside. Okay, what is inside here? Okay, inside is this one. What is W1 x? This whole thing. Okay, in terms of x1, because this is the first data point. X1, okay, minus T1. Okay, so what is the term here? When you take the derivative of this one with respect to W1. So this one is not in terms of W1. This one is yes in terms of W1. This one no. So that is 0. That is 0. That is 0. And that is 0. Okay, so you are remaining with this one. So you take the derivative with respect to W1. This one with respect to W1, what happens? Okay, partial of this with respect to W1. This one will cancel. And then you're remaining with x1 to the 1. Okay, next, the same thing here. So this 2 goes here, cancel again. And then this one, and then you put here, you rewrite this one, and then what's inside, okay, in terms of W1, so that is x2 now, x2, 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 x2. So still x2 to the power 1, okay, and so on here, xn, 2 comes out here, and then 2 cancels. So you have xn to the power 1. Okay, so that means that when it's this one, when you do the derivative, the exponent of 2 here, and then the 1/2 disappears. So this one, no more 1/2, no more exponent 2. Okay, and then we repeat this, the summation of all the same thing, summation. So the same thing, the summation of this, okay, minus the t, okay, so plus the summation of this minus the t multiplied by x1. X1 in this case here, this is the, because we are looking at, this is x1, x2 up to xn. Okay, so this one goes up to 1 in terms of the data point. So now you have xn where n goes to 1 to n. Okay, so now the whole, when you rewrite this whole thing, it is just this summation where each term is multiplied by the corresponding xn to the 1. So that means here also xn, 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 where n goes from 1 up to big N. So there, so this one, y in terms of xn and w minus t of the n, where the small n goes from 1 to big N. So this one is correct, multiplied by the x of small n to the power of xi, where your xi is this coefficient of that, the same as the order of x. The same is the coefficient of w and the order of x1. Coefficient of, because we are talking at coefficient of w, which is the order of x1. Okay, I mean the order of x1 up to xn, and this order is always 1 because we are looking at coefficient w. Now, if you want, I mean, you're looking at coefficient of w1. If you want to change this into terms of w2, okay, now we are looking at I is equal to 2. If your I, everything else will remain the same now in terms of W2. So this one now becomes 0 because this is not in terms of W2. Only now, this term is the one that applies now. So the x1 up to x2 up to x big N remains. But the only thing that changes here is the exponent here, which is your I. I in this one becomes 2 because it is in terms of W2 if we take the derivative of this with respect to W2. Okay? So now that's why this I here corresponds to the I here. Okay? And all the n's here corresponds to the n index, small n index, which goes from 1 up to big N. So now this is your derivative. Okay, you can try the exercise at home to convince yourself that this is really the derivative. Okay, so another way of expressing this term is we just want to express this in terms of the summation of the polynomials here, which is this one. Okay, so we're just changing this into this summation. So that summation is, this term is substituted by this term, okay, minus Tn, okay, and then that's it. You have the summation of n is equal to 1 to big N multiplied by this one. It's exactly the same term. The only difference is that in terms of y, x into w, you have the summation. There's a reason for that so that we can spell out everything. Okay, so any questions in that one? In the derivative, I think that one is straightforward. How the derivative was computed. Okay, now let's move on. Okay, now let's have an example so that we will learn exactly what's going on. So, what happens here? Shift F5. Okay, let's have an example. So, are we still recording?
Yeah, it's still recording.
It's still recording. Okay. Thank you. Okay, now, so let's have an exercise where we have your polynomial function, okay, of the second order. So that means that W0, this one, xi to the 0, W1, xi to the 1, and W2, xi to the 2. Where your I, okay, is the index of the data. Where your I in this case goes from, this is xi and ti, where your I, okay, goes from 1, 2, 3, 4, 5, 6. There are 6 data points. Okay, and we will have these 6 data points of input x and our target value t. Okay, then we are going to use a second order polynomial or a parabola to estimate this kind of function. Okay, so what is the parabola that gives us the closest estimate, estimate of this data set? Okay, so now because we are looking at parabola, there are 3 weights that we are looking at. Okay, we have to compute for the 3 weights, and then we will compute the error, the same thing as we did here, this error term. So this error term, sorry, I didn't emphasize it. I was concentrating more on taking the derivative. So your derivative, whatever derivative you have computed, is included here. So it will be a vector of derivative of the error function with respect to W0, derivative of the error function with respect to W1, derivative of error function with respect to W2, and so on, derivative of error function with respect to Wn, which is the order of the polynomial. Okay, so now then multiplied by, this is your learning rate, normally around 0.1 learning rate. Okay, now your W is the initial W, you can just randomly initialize it. Okay, There's no big issue there. Initialize your values, and then this is a vector, of course, and then based on this new computation of the error multiplied by the learning rate, and then you subtract it with the current W to get your new W.